Oh, welcome once again to Sunday Science, everybody, or Science Sunday, however. It doesn't matter which order the words go in. It's Sunday and there is science to be had. On this week's episode, we are going to be discussing something that oftentimes is misrepresented in a very shameful way from my standpoint, because without it, we would not exist. With too much of it, we will not exist. It's something that we interact with on a daily basis, and there's really no reason to be concerned about the fact that we interact with it and need it, and it can kill us. So,
no reason for concern.
No, it's a normal daily thing, and like I say, without it, we wouldn't exist. So, it's a very, very normal, very natural thing that takes place in our universe. And if you haven't guessed it already, we are going to be talking about what is radiation and how it affects our lives, what do we use it for, how we came into understanding it, all those fun things. So, just thanks one more time for joining us. I think it's going to be a spectacular episode. Like I say, radiation is misrepresented in the general public to such a degree that it has many people terrified and many others making it sound like it's hot potatoes, who cares? And in a way, it actually is hot potatoes. But we'll get to that. So, in general, when people sit down and they talk about radiation, it's such a misidentified, misrepresented terminology. It really should be, in my opinion, kind of redefined to make a statement about different types of what radiation is, because in essence, all that radiation is energy being emitted from a particle. So, obviously, that can mean a tremendous amount of things. Now, basically, everything kind of boils down to two different types of radiation, and that's ionizing and non-ionizing. And what that means is that the energy being emitted from one particle or group of particles in a molecular system, they give off either enough energy to disrupt the electrons in other atoms, or they do not. So if it's ionizing radiation, it can disrupt electrons in an atomic shell. If it's non-ionizing, it won't. So with that, I mean, there's a tremendous number of areas that could go, and it's a really broad subject. So I'm just going to be touching on some of the generalities that a lot of people have a misconception in, and some of the areas where sitting down and maybe going to somewhere like Khan Academy and learning a little bit more in depth on your own is going to be very beneficial. I, for one, love Khan Academy. They put out a tremendous amount of educational resources for free. If you haven't looked into them, I absolutely suggest it. And Sai, if you wouldn't mind, could I have the breakout chat link?
Oh,
that would
sure.
definitely help.
Sure, coming up. One second
awesome.
here. Here we go.
Excellent. Thank you very much.
Not a problem.
Always helps to have.
Yeah, nice to see if folks have questions for you or anything of that sort.
Right. Indeed. So with the types of radiation that are most concerning to people, I'll go ahead and jump into those ones. And while they're concerns to people, realistically, there are certain things that, as long as you understand what it is that they are, where they do take place, it's really not as scary of a subject or topic matter as you may think. Oh, and thank you, Brian Stevens, for popping up the Khan Academy link in the public chat. That's awesome. Much appreciated. So with when it comes to particle radiation, It's all ionizing radiation. There are 3 sets that I'm going to touch on because the other 2 are part of another field of radiation that is for later in the show. So the first 3 to really think of when it comes to the decay of a particle and the radiation that it presents is it's generally what people have a question about or an unknown about or a fear concerning. That would be alpha decay, beta decay, and neutron decay. So all of these things take place in elements that are unstable for one reason or another. Maybe they have too much mass, maybe they have too much energy. Either way, they do degrade and they do break down. And touching on that a little bit more, all elements go through a procedure such as this. Everything decays. Everything breaks down. The carbon in your DNA, if it didn't decay, wouldn't be there. It's how we actually get to utilize radiocarbon dating. So there's again, not a huge reason to fear what it is that these types of decays are. It just means that an element is shedding particles, be it electrons, be it neutrons, be it neutron-proton pairs. It's a natural process. You're around it all day, every day, and it's, don't go climbing around inside Chernobyl by any means, but you're around this stuff all the time. So with alpha decay, excellent, thank you.
Sorry, it took me a little bit to chase that one down. Honestly, I thought you were going with alpha, beta, and right to gamma, but no.
No, I wanted to skip gamma and X-rays because they do lead into the electromagnetic spectrum, and that is, well, it's just for later.
Gotcha.
So with alpha decay, what's happening, let's say you take one that probably everybody seems scared and worried about, uranium. Uranium goes through an alpha decay process in which it decides, I can't have all of this mass in me. I can't have all of this matter and this energy anymore. It's too much. So it spits out the nucleus of a helium-4. So that's 2 protons and 2 neutrons. Now there's no electrons on that nucleus, so it's not actually helium-4, it's just the nucleus of a helium-4 atom with no electrons. And alpha particle decay is extremely common with just about anything that you could ever imagine coming into contact with. I mean, uranium decays into thorium, thorium decays into radon, not radon, oh, darn it, my brain just went blank. No, it happens. Anywho, it's a normal decay process, and it's not directly harmful unless you decide you're going to be an idiot and ingest it. As the penetrating distances diagram that SciStrike was so kind to put up, and alpha, I mean, you could actually have raw uranium ore wrapped in paper in your house. It wouldn't harm you. Now, granted, there's always a very good possibility you could pick up that sheet of paper, forget to wash your hands, accidentally ingest something that you shouldn't ingest, and it's going to be harmful. It will be harmful. So don't do stupid, but also be aware that there's a wide world of what radiation is, how far it can travel, the sorts of damages it can do. And as I said earlier, we're subjected to radiation all day, every day. Chances are you've eaten radioactive foods and never even realized it. Our entire life cycle couldn't actually exist without radioactive decay. So it can be a little bit weird to think about, but it's part of life, and it's part of the universe that we live in. So understanding it is better than fearing it.
Especially since there's not much we can do about it.
Indeed, it's a process that's going to happen whether we like it or not.
Indeed.
Eventually, all carbon-14 will break down into half as much carbon-14 and a bunch of nitrogen instead. But getting a little ahead of myself on that one. So then we move up from alpha decay to beta particle radiation. And again, this is something that we experience on a regular basis. Beta particle radiation is quite literally when an electron is stripped from an atom. So it can do damage cellularly, not really enough, I would say, to get wildly concerned with, because as a couple of episodes ago, you may remember some of the homemade experiments that both SciStrike and myself are building. Well, we're inducing our bodies with beta radiation by sitting down and playing with Jacob's ladders and Tesla coils and Van de Graaff generators. Again, it's just one of those things. You're going to be around it. You are around it. Your cell phone has it. Your computer has it. There are levels of beta radiation, obviously. Like anything, too much of something can always be bad. That's just a fact of life. Beer is fun. Too much beer will kill you. Driving is fun. Driving too fast might kill you. It's one of those things. Moderation. Now, granted, moderation doesn't work with all things when it comes to radiation, and especially when you start talking about, as I said, I'm going to skip gamma and X-rays because they fit into another class that's a little bit more concerned with the types of sciences that I'm very, very much involved with. So when we do jump over X-ray and gamma radiation and we start talking about neutron radiation, now we are getting into something that you really probably don't want to be around. So what neutron radiation is, it's when an atom is going through a fission type process and it releases a free neutron. So talking about the alpha decay rate, you're talking about effectively helium-4. It's very heavy. Again, it doesn't have the electrons. It's just the particle itself of 2 neutrons, 2 protons. It's incredibly heavy, so it doesn't travel far and it doesn't take much to stop it. Beta radiation's an electron. It's a lot lighter and it's capable of moving at higher speeds. It needs a little bit more to actually get stopped. Neutron radiation, on the other hand, you're starting to talk about energy levels that, if you remember last week's episode with particle accelerators, you're dealing with hundreds upon hundreds, if not tens of thousands of electron volts. And that's just to get the thing to move a little bit. So with neutron decay, you're talking about extraordinarily high energy levels. And, well, the little graph here does show that it's stopped by concrete. I want to explain a little bit more about that. With neutron radiation, the reason why concrete is such an effective barrier, and even water itself is a very effective barrier, is you're looking for something that has a very high hydrogen content within it. Those hydrogen molecules, and they absorb that additional neutron at a rate that's actually feasible for shielding against it. So if you sit down and you watch videos of a certain person who doesn't really like having his name mentioned without consent, you'll see he's always standing behind incredibly thick concrete walls in his videos, and that's due to the neutron radiation within a nuclear power plant. Concrete is a very effective barrier. Water is a very effective barrier. Neutrons want to join a molecule, and it makes neutron radiation far more dangerous than alpha and beta types of radiation, simply because alpha and beta radiation don't necessarily harm you upon direct contact. They can. It takes an extreme amount, but there's always the possibility for accidental ingestion, and that's where they become very dangerous. However, neutron radiation, having random neutrons go ahead and join the atoms in your body, it can actually irradiate other materials that are within its vicinity. And accidentally having your body become radioactive is extraordinarily destructive to your DNA. It doesn't go over very well.
Important safety tip.
Indeed. If you work in a nuclear reactor, I'm sure you don't need me saying this. If you don't, maybe you already know it. And if you've just always been curious, hopefully I can help shed some light on some of it. All right, so like I say, I'm going to be skipping gamma and X-ray radiation because they fit into a different field that we're going to touch on here shortly. But before we do that, why don't we look a little bit at our history and understanding of radiation and sources of radiation throughout history. I'm sure a lot of the viewers here are already aware of Marie Curie and the work that she did. There's a lot more at play, though, than just, hey, I eventually got sick and passed away. She was a Nobel laureate 2 times over, both in physics and chemistry. Absolutely phenomenal work. And without some of these early pioneers doing the work that they did, it would be very difficult to really admire the extent that some people are willing to go to for a new and a more cohesive understanding of the world around us. There was, from the get-go, from the beginning with their experiments with playing around with dumping different currents into vacuum tubes, which this actually goes prior to Madame Curie. And I always say his name wrong, but I believe it was Wilhelm Röntgen, if I'm not mistaken. He was using vacuum tubes effectively to see what is light, what is not light, and getting things to project onto a screen, even though it was blocked. There shouldn't be anything visible here. And I'm sure everybody has obviously heard the term X-rays. It's up on the screen already. And one of the funniest things with the entire term X-ray was that it was dubbed an X-ray as it was an unknown ray, being viewed, being able to be worked with, being able to be sampled. It was simply an unknown ray, thus it was dubbed an X-ray. It was unknown. And still, what, 130 years later, 140 years later, well, they're still X-rays. Now we know what they are. We have a little bit better understanding, but, you know, that's the way that the scientific community works. Sometimes you find something that maybe you shouldn't have found, but it leads to amazing things happening later in its time. So, well, we are talking about Madame Curie and all of the work that she did utilizing radium, things of that nature, actually discovering a couple of elements all on her own. There's a decently well-known quote from her that I'm going to go ahead and read real quick, and it goes as follows. "We must not forget that when radium was discovered, no one knew that it would prove useful in hospitals. The work was one of pure science, and this is a proof that scientific work must not be considered from the point of view of the direct usefulness of it. It must be done for itself, for the beauty of science, and then there is always the chance that a scientific discovery may become, like the radium, a benefit for all mankind." I have always really admired this quote, because there are many of times, especially immediately following her untimely passing from anemia, that scientific discovery has done some harm, and it doesn't need to be that way. It is that way because humans are kind of a messed up, war-hungry primate, and well, that's the way of life, I guess. But the benefits sometimes of tragic works such as this that have led to horrible weapons, things of that nature, I don't need to get into. Everybody already knows that end. But the scientific research initially, maybe it could have been moved this way, moved that way, created this, created that, but fundamentally, the pure science behind the discovery, behind the work, behind an understanding of our universe to that better of a scale, it can lead to very great things.
Indeed. That's a very inspirational quote there. I did like that. Did you want a fun fact about Madame Curie that you probably already know?
Sure.
Fun fact. Here we go. It is one of my favorites too. Madame Curie. Sounds very French, huh? She is not. She was not French. She's Madame Curie was a nice Polish girl. Her maiden name was Maria Sklodowska, from Warsaw. So there's a fun fact about Madame Curie, the fine French woman from Warsaw.
Very awesome.
Okay, sorry to interject. Carry on.
No, by any means. Factoids are always great. Okay, so back to the fact that you are living in a world filled with radiation. Obviously, I'm avoiding the electromagnetic spectrum for the time for the obvious reason of being around it all the time. But even with traditional ionizing radiation and the fact that I stated earlier, you quite literally could not live without it, and you've eaten it on a regular basis, chances are. I don't know what everybody else's diet consists of, but when I get a muscle cramp, I generally have a tendency to go, I need a banana. Well, once you know why you're wanting the banana, it's because of the potassium in it. Well, potassium-40 is actually decently radioactive. Yes, bananas are radioactive, so are carrots, and as I said at the beginning of the show, literally hot potatoes. Potatoes actually have a large amount of potassium-40 in them, and they as well are radioactive. Now, without potassium-40, and you'll have to excuse me, I'm being a complete geek and standing up and fingering my way through a chart of the nuclides right now. Nope, went too far. Oh, where are you? 40. Well, anywho, I'm not going to try and finger my way all the way through a chart of the nuclides. They're freaking enormous. But again, this is one of those reasons why I always press anyone that's interested in chemistry or in just basic life sciences in general, I would say, pick yourself up a good chart of the nuclides, because the wealth of information within them is so much more vast than just a periodic table. The periodic table is beautiful. It's wonderful. A good chart of the nuclides, though, it just has so much more information. So when I'm talking about potassium-40 or, U-238 or iridium-11, what we're talking about is the number of protons and neutrons in their nucleus. So you can have the same element have a different number of protons and neutrons. You can have groupings of atoms. Obviously, carbon-14. Carbon doesn't just float around as a single atom. It likes to be in a nicely tight, packed group that also radioactively decays over time, which is where radio-14 carbon dating comes into and gives us a pretty good timeline for almost 50,000 years worth of history. Other things such as that exist. I believe it's oxygen-8 is the oxygen in water, and oxygen-6 is kind of its decay particle. I could be wrong in stating that it's a decayed state. I never really understood that one as well as I probably should, but I don't understand a lot of things as well as I probably should. But these things do exist all around us, and they decay at very specific rates. And they give us a good ability to judge elapsed time. They give us a good ability to sit down and take something that is radioactive, such as potassium-40, and track what its half-life is. And when you hear someone talk about a half-life, what that is that if you have a sample size, let's say 100 atoms of a sample. Now, granted, that's obviously not even really a molecule, but what its half-life is the amount of time that it takes for 50 of those 100 atoms to decay to a lower state. So effectively, let's say you take the carbon-14. If you have 100 atoms of carbon-14, after a little over 5,000 years, you're no longer going to have 100 atoms of carbon-14. You're going to have a decayed byproduct of carbon-14, which is going to be half as much carbon-14 plus, I believe it's nitrogen-12. I could be wrong on that. I'm trying to pull a lot of this out of memory, so I could be wrong. But anywho, that's the effective definition of what the half-life of something is. So when we're still talking about this ionizing type radiation, where the concern lies is the amount of time that its half-life has. So if you have something, this is where you kind of need a nuclear physicist and not someone like me that just really likes talking about this stuff and learning about this stuff. There's certain amounts of things out there that their half-lives are so incredibly short. The amount of energy being released by that product or by that material is so high that that's when you're talking about dangerous isotopes and things of that nature. So since we're right about at that point, I say we go ahead and let an expert take over, and we can take a quick listen from Dr. Don Lincoln from Fermilab, as he can just explain certain things at a level that I may not be able to.
Alrighty, coming up. Here we go.
Radiation can be a scary word for a lot of people. But just what is radiation exactly? I mean, you probably know that it's responsible for such 1950s monster movies like Godzilla, but that doesn't tell us much. Radiation, in the sense that we normally mean the word, was discovered in 1896 by Henri Becquerel when he discovered that uranium could fog a piece of film. But even that definition of radiation is incomplete. So what is radiation exactly? Radiation is the emission of energy by a substance. There are lots of kinds of radiation. There is electromagnetic radiation and nuclear radiation. Electromagnetic radiation encompasses such things as radio waves, microwaves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. These are all pretty familiar and aren't what we normally mean when we talk about radiation. I mean, microwaves can cook things, and ultraviolet can give you a sunburn. So it's not like electromagnetic radiation can't be dangerous, but it's generally not what people mean when they talk about radiation. Actually, gamma radiation is an example of that kind of radiation, but we'll return to that in a bit. When people talk about radiation, they mostly mean nuclear radiation, which is when subatomic particles are emitted from the nucleus of atoms. I should also say that nuclear radiation is sometimes called ionizing radiation, as it's energetic enough to knock electrons off atoms. But I'll call it nuclear radiation to remind you of the radiation's origin. And there isn't just one kind of nuclear radiation. There are at least 4 different kinds. There's alpha radiation, beta radiation, gamma radiation, and neutron radiation. Each of these types of radiation have different characteristics. Alpha radiation is when an atomic nucleus shoots out an alpha particle, which consists of 2 protons and 2 neutrons. If you dust off your chemical knowledge, you'll recall that the nucleus of a helium atom contains 2 protons and neutrons, so alpha radiation is when a radioactive element shoots out a helium atom minus the electrons. Beta radiation is caused when an atomic nucleus shoots out an electron. We could call it electron radiation, but the name was invented before we identified the emitted particle as an electron. It generally occurs when a neutron in an atomic nucleus turns into a proton and an electron. The proton is kept inside the nucleus and the electron escapes. Gamma radiation is when an extremely high energy photon escapes the nucleus. In a sense, this isn't much different than a nucleus emitting ordinary light, but the much higher energy involved means that the gamma ray can damage surrounding material. Gamma rays are often used in comic books to give superpowers to unsuspecting spectators. By the way, X-rays are similar to gamma radiation in many ways, but less energetic. They're like gamma radiation's younger and less successful sibling. And then there is neutron radiation, which is just the emission of a neutron. In a sense, this is the most dangerous type of radiation, but as we will see, that's a subjective statement. So these are the different kinds of radiation that one encounters in nuclear physics. But as we will see, they have radically different properties. This isn't a radiation safety video, but it's important to know, at least broadly, what you need to do to be safe around radiation. Perhaps obviously, the easiest thing to do is just get very far away from it. Just like a fire seems cooler the further you get from it, distance is the easiest way to reduce your exposure to radiation. However, that's not always possible. We live in a radioactive world. Bananas are radioactive, as are Brazil nuts. Heck, you are radioactive. I made another video discussing levels of radioactivity, and if you watch that, you'll understand that low levels of radioactivity are not inherently dangerous. But there are things you might encounter that are more dangerous. Things like dental x-rays, for example. Now, don't worry about dental x-rays. They give you a very low dose, and they're definitely worth having. But if you're, for an example, a dental hygienist, you might encounter lots of x-rays and want to protect yourself. So it's important to know about the ways in which you can shield yourself from various kinds of radiation. Alpha radiation consists of heavy and slowly moving particles with a lot of electrical charge. These properties combine to make them easy to stop. You can stop alpha particles using a single sheet of paper. Here, I'll show you. Here is a sample that emits alpha particles in a Geiger counter. The paper stops the radiation. Beta radiation consists of light and fast-moving particles with electric charge. This means that they can be stopped by reasonably thin plates of material. For instance, we see here that they can be stopped by a thin metal plate. Gamma radiation consists of fast-moving particles with no electric charge. This means they emit no electric fields to interact with matter. They are therefore much harder to stop. To stop gamma rays, you need a heftier chunk of dense material like lead. This is also true for X-rays, which is why they put a lead apron on you when you're getting dental X-rays. Neutron radiation consists of pretty heavy particles with no electric charge. Since they don't interact with atomic electrons, they can travel long distances, say hundreds or even thousands of meters in air. The way to slow them down is not so intuitive. You have to use something with a lot of hydrogen in it, like water or plastic. The neutrons hit the protons in the hydrogen nuclei and knock them out. This stops the neutrons, and then the charged protons are stopped quickly, much like alpha particles are. By the way, given the clicking noises you heard, you might be wondering if the technician doing the demos here was in any danger. The answer is no. The radioactive sources we used were real, but they were weak. This diagram shows you roughly how to shield the various kinds of radiation. It summarizes what I just said. So I've told you about how to protect yourself from radiation, distance and shielding. And for shielding, I've told you what works for what kinds of radiation. But what if you can't move away or get shielding? What impact do these types of radiation have on human tissues? This is kind of interesting. It turns out that the different types of radiation have distinctly different consequences in terms of biological damage. In order to figure this out, scientists took different kinds of radiation and aimed them at various kinds of tissue and saw how much biological damage occurred. They then came up with a number that would account for the differing amounts of damage observed. This number is called a quality factor, or just Q. If Q is 1, that means there's no adjustment. If Q is greater than 1, that means that this particular kind of radiation is biologically more dangerous than other types of radiation. So we see here a chart that shows the Q factor for different kinds of radiation. We see that gamma and beta radiation and X-rays have a Q factor of 1, which means that they don't have an enhanced damage capability. But slow neutrons have a Q of 5, which means that for the same amount of absorbed radiation, more biological damage occurs. Fast neutrons have a Q of 10, and alpha particles have a Q of 20, which means that they do more biological damage than other kinds of radiation. That last one is kind of weird. I mean, alpha particles are easy to stop, but do more damage in living tissues. But if you think about it, this makes sense. When an alpha particle stops, it stops hard, and it deposits all of its energy in one place. This means when it hits a cell, the local damage is extensive. This is especially true if you're unlucky enough to inhale alpha-emitting radioactive dust. That's extremely dangerous. So I hope that this video kind of gives you an idea of the diversity of possible kinds of radiation. I mean, there isn't a single kind, and that means that if you want to understand radiation and how to react in a certain situation, you really do need to become informed. However, that does take work because, in the end, understanding radiation is like your Facebook status when you're deciding if you want to get back together with your ex. It's complicated.
Okay, go ahead.
Oh, I got nothing. Go
ahead. I suppose I should touch on the fact that at the beginning of the episode I did state how alpha particle radiation is extremely harmless. And even though it does actually have an extraordinarily high rating as far as the damage that it can do to cells, alpha particle radiation is something that you experience walking through the park. It's something you experience going to work every day. And luckily, as long as it's not inside of you, alpha particles can actually penetrate dead skin cells. So, you know, don't cover yourself in uranium ore and take a nap.
Okay, another important safety tip.
I'm sorry. There's some things when it does come to yes, alpha radiation is extraordinarily bad for your cells, but it basically has to be inside of your body. Hence why Dr. Dawn was talking about accidentally inhaling particles. That's where you start getting into real dangerous realms with particular radioactive substances. Is you accidentally inhale it, it gets into your body. Certain things, let's say radium, for example, your body thinks radium is calcium effectively, so it winds up in your bones. Well, that's real bad. You don't want radium in your bones. So it's a tricky game. It's a tricky subject, but now that we got through the general ionizing, yes, I left out gamma radiation from ionizing radiation because while gamma radiation is technically ionizing and X-ray as well can be, they are part of the electromagnetic spectrum. And this is the radiation that we are blasted with all day, every day, even in the middle of the night, just because a lot of people think of the electromagnetic spectrum as being visible light with a little bit on the other side we can't see and a little on the other side we can't see. The electromagnetic spectrum is I don't know, 100 times more broad than what we actually see. So electromagnetic radiation... Oh, thanks for zooming in on that. That's very helpful.
I figured you might not be able to get a clear view of that.
Oh, that helps tremendously. Yes, well, so what we consider to be our optical field of view, from deep violets to bright reds and everything in between, it's an extraordinarily minuscule portion of the electromagnetic spectrum altogether. So with EM radiation, what it is that we're talking about is obviously photons being emitted from an atom. Now those come from two places, as you saw in the video earlier. Gamma radiation is still part of the electromagnetic spectrum, but it is much, much more dangerous than visible light. Obviously, it's photons being emitted from the nucleus of an atom, as opposed to an electron discharging a photon. I shouldn't say discharging, that's not the right word. Anywho, this particular type of radiation, and why it is that the word radiation, I really think, needs to be kind of redefined at some point in time to... Or maybe not redefined, but taught in a fashion of electromagnetic and ionizing, because part of the electromagnetic spectrum is ionizing. It's incredibly high energy particles, and I don't want to try and get into the math of, C equals lambda over nu, or C equals lambda nu, sorry, not lambda over nu. I was starting to break the equation down in my head the wrong way, going lambda equals C over nu, but hey, anywho. There are incredibly high energy particles in the electromagnetic spectrum that can actually knock electrons clean out of their orbitals and be very destructive, and that is in the gamma ray spectrum, gamma ray region of the spectrum. Now, our visible light spectrum is, it's absolutely puny when you sit down and consider it. I think the entire visible spectrum is something to 400 to 700 nanometer wavelength. Again, it's been a while since I've looked into exactly what it is that a person can see, but I believe it's somewhere around 700 to 400. So the entire spectrum itself covers, you can see from the graphic represented, everything from, even 10 to the minus ninth, that's not even enough. It goes slower than that. Anywho, what it is that's talking, what those numbers represent, that frequency. What that frequency is an actual measurement that we're able to sit down and, we can actually measure these sources and what is it, how do they work, why do they work. And in the electromagnetic spectrum, as I kind of spouted earlier, C is equal to lambda over nu. And what that means, C is our cosmological constant, obviously. It's what we call the speed of light. And the best reason I can ever sit down and state as to why it's called the speed of light is because all electromagnetic radiation, based upon its frequency and its energy, it's always equal to the speed of light. So C equaling lambda nu is, lambda is a meter per second, and nu is the frequency in hertz. And irregardless of where the spectrum is, so very, very slow-moving light is going to still move at the speed of light, as is very, very fast-moving light, because they have kind of this intrinsic property that they share with one another. Photons always travel at a certain speed. They just travel at a certain speed with a different waveform and a different frequency, which I guess that's kind of saying the exact same thing, but
indeed. And
yeah, I wasn't actually trying to start breaching that subject. I was just trying to think about the radiation, blah, blah, blah. So obviously getting up into X-rays, as stated earlier, yes, long-term exposure to X-ray radiation can be damaging. Short-term exposure to gamma rays can be extremely damaging, and I'm sure there are a lot of viewers here that also already know about gamma ray bursts and the potential hazard that they have, and the basically zero potential of ever actually being hit by a gamma ray burst within your lifetime. Yes, gamma rays are extraordinarily damaging. They can be found in a lot of places here on Earth in laboratories where we produce them. But again, unless you already work in that situation, you're probably never going to encounter them. I wouldn't worry about it. If you're worried about a gamma ray burst coming from an exploding neutron star in outer space, don't hold your breath.
It's like, well, the good news
the universe is vast, and
the good news
we're
is we wouldn't know about
small
it.
by comparison.
We wouldn't know about it. I mean, it's it wouldn't be a slow process.
Obviously, there's a tremendous amount of work that we're able to do with the electromagnetic spectrum, and if you recall a few episodes, maybe more than a few episodes ago, space observatories, and showing how it is that composite photographs of interstellar bodies are, well, how it is that they're viewed from all of these different sources, from microwave all the way through ultraviolet. I'm actually kind of glad that as humans, our brain only perceives a very, very, very small portion of the electromagnetic spectrum, because it would be a really weird place to live in if we could visually see any more than what we do. I don't know about the rest of you, but I'd probably be scared to death if I could see my cell phone transmissions and my Wi-Fi connections. Doesn't sound like fun. I'm glad we view a very, very, very small portion of the electromagnetic spectrum, but the work that we can do with it and the discoveries that we can make utilizing the full width of this particular source of radiation, whether people want to consider it radiation because it is radiation, whether people don't want to consider it radiation because they don't want to think about the fact that every time they go out into the sun, they're irradiating their bodies. Radiation is a very, very amazing part of physics, and it's never going to stop, and there's nothing we can do about it. So until the universe goes cold and dark and we go into a decay rate that doesn't care that black holes even exist, radiation is going to be here. And it shouldn't be viewed as something that is scary. It should be viewed as something that is a natural process in the natural order of the universe we live in. And it's actually quite a beautiful thing because it allows us to see. It allows us to stay warm when it's cold. It allows us to move through space and across the planet. It's truly a wonderful thing that should not be feared if properly understood.
Well put.
I think that's about all I have for this particular episode. Is there anything you want to toss in, Si?
Oh, no. I actually, you covered the subject fairly well. The whole respect, not fear, is definitely a good way to look at it, and the usefulness of radio.
You on mute, Si? I can't hear you.
Oh, okay. No. Hello. That's odd.
I can't seem to be able to hear anything.
Huh. Unusual. Is the live chat, folks? Can you hear me? Okay, Brian hears me. Huh. Maybe Andy inadvertently muted me. Well, anyway.
Yeah, I can't hear you at all, Psystrike. I'm not sure what in the world's going on there.
Okay,
I would unplug my headset and plug it back in, but if I do that, I'll get kicked out of the Hangout.
Okay, here, I'll type for Andy. There we go. All right. And, okay, Sue says you can hear both of us. Not sure what happened with Andy's receiving of audio, but as luck would have it...
I might have to rejoin. Let me try unplugging my headset and seeing if that helps. If I get booted, just, let me back in.
Okay. All right. If we're experiencing technical difficulties, please stand by. Oh, and Brian, thanks for the speed of gravity a little while back. That was that was a good comment. And hopefully Andy shall be jumping back in shortly. And actually, Andy said it sounded like he was just about to wrap it up anyway. Here, let me just type it out for him. There we go. Yeah, we'd gotten to the point where Andy was asking if I had anything to add, and actually, since Andy's both knowledge and experience in this particular area exceeds my own, well, I have nothing to add to Andy's presentation, which I believe was most informative. All right, well, you know what? Hopefully Andy will let me know if we should just close it or continue. But in the meantime, if you want to interact with the any or all of the Science Strike Force team, we now have a Discord server, and the link is in the. Andy may be back. The link is in the description, and feel free to join. Oh, look at that. I wrote Discourse server. That's not right. Let me fix that. Discord. There. That's right. Okay. Yeah. We have a Discord server. Feel free to join. You can communicate. There's text chat, and if anybody wants, there's voice chat, and then, it'll show you who's online, who's not online, all that sort of thing. I'm sure you all know about that. And let's see. Bring the public chat back up. All right. Andy says he believes his headset's done. All right. On that note, we might as well wrap it up. And look at that. We're just coming up on an hour. And yep, we still have no Andy. Oop. Let's see. There was the sound. You back, Andy? Oop. Andy's back.
Okay, I can't hear anyone, but I see the little sound bars like I'm back.
Okay.
Unfortunately, I can't hear anything. I think something's wrong with my headset. Thanks, everyone, for joining us for Sunday Science, and I will fix this issue so it's not around next week.
Okay.
That's about all I have without being able to hear anything. Wish you guys all a good remainder of your weekend, and thanks for joining us.
Indeed. Thank you very much, everybody. And on that note, do have an enjoyable week. See you next time, everyone.